So everything I said today is based on my joint work with Rapcak and Soibelman and Zhao. So let me start the revision of my talk. So there's some overlap of my setting with bounds, so I'll try to set up things differently. So I take x to y. So this is the where x is a local toric Calabi-Yau threefold, and a local, I mean, it's an open neighborhood in a compact Calabi-Yau. So F is a resolution of singularity, and this space Y is fine. The small rapid solution. And some basic examples. Then we can take X to be C cube, and this definition is identity, and Y is C cube. Second example, the result of the manifold. So X will be the total space on one, or -1 plus only 1, where Y is equation XY equal to W. And there's another example. It's a total space 1 on -2 plus 4. So this is the cotangent bound of P1 plus the trivial. And so where Y is upper, it's XY equal to squared. That's building blocks. And more general, you can group those three types of things together. Okay, so now I'll fix B to be some preferred sheaf. X. So for example, the favorite one, you can take B to be or X. Okay, so I want to consider the following modular space. So this modular space is in the paper of Nakajima. So they call it the modular perverse coherent system. Okay, so I'll just denote it by M. So M is parameterizing such pairs F and S, where F is the perverse coherent sheaves. So due to the time constraint, I will not define this, but I will say, so for such resolution singularity, so you can define some T structure, and so the perverse coherent sheaves will be the heart of that T structure. So this form a building category. This have equal X. And so S is our framing, so S is a section of the F. And such moduli satisfies some impose some stability condition. Okay, so this is the moduli of sheaves on the threefold. Okay, so often, so this moduli is a critical, you can write it as a critical locus of some potential function, critical locus of potential. So let's see a few examples. So in the simplest case, when X is the CQ, and so the perverse coherent sheaves, we just get the coherent sheaves on C3. Okay. And if I take my preferred sheaf B to be for X, and some of the stability condition is gonna give you Hilbert schema points C3. So this is occurred in Bufan's talk already. Right, so it's parameterizing points on C3. So I'm interested in the combinatorics, the torus fixed points. I take the maximum, right, so C star to the cube. So the torus fixed points will give you all the three definitions. This example. one example. So another interesting example is we're taking x to be 0. And so now I'm gonna fix a curve beside x. So I want the curve to be fixed. I will write this as C of lambda, where lambda is a triple partitions, lambda 1, lambda 2, lambda 3. And so this curve means the outgoing partitions is given by lambda 1, lambda 2, lambda 3. With our partitions. So what does this mean? So maybe I can be a bit more precise. So if so this curve that if I look at the ideal sheaves, so that's ideal in this polynomial range with three variables. And because I'm taking t fixed, so this guy will correspond to a 3D partition. So I can localize at the three directions and see localize at xi. So it's still the localized thing. And so this localized guy will see the three partitions. So this corresponds to. Right, so if I fix a curve, a relevant modular space, relevant to my talk, the following. So this PT modular space with this ray with fixed inequality given by lambda. So this is a modular parameterizing stable pairs. That's S, where I want the support of the sheaf to be C. And so S, the section, is finite codimension. Dimension is the COHA S 0. That's a modular, PT modular space. And in this example, it can be very concrete. So maybe I'll just draw one picture. So if you look at this T, and there's a torus fixed point. So this is a concrete of the box. Okay, so maybe I'll draw one picture. So just for illustration purpose, if I look at this one, 0, 0, and so the PT box counting is the vacuum configuration. So I look at this 2, 1, this 1, this 2, this 3. So so this partition in the negative direction of this one. The negative direction, and so that's a vacuum configuration. So there's a rule to put boxes inside the cylinder. So this is cylinder in the negative direction, and so if you want to do one box, so there are 2 possible configurations containing only one box. Meaning I could put negative direction. So I would put the one box on here. Or I put the box. PT counting rule says this one is not allowed. So if you want to put the box here, So this. If space box within those two has to be them. Okay. All right. So I give some examples of those modular space. And so for me, so I'm interested in the homology of the modular space. There is values in this vanishing cycle functor. So as Gufang said, so this is the vector space. So you can think this is the categorified DT. Because the Euler characteristic gives you the DT invariant. And it also has nice combinatorics. Those T fixed points will label a basis for this vector space. Okay. Right. Okay. Okay, so I have this perverse coherent sheaves. This is the ability category, and by a general theorem, there exists activity vector bundle T on X. So what does this do? So your ability category. So this is the isomorphic ability categories to modules of the endomorphism. Okay, so it's isomorphic module category with explicit algebra, and this algebra is the Jacobian algebra of a quiver with potential. Okay. One has lots of examples. This quiver with potential. Okay, and so for arbitrary quiver with potential, there's an abstract construction by Kontsevich and Soibelman. So out of this data, so they have a cohomological Hall algebra. I just denoted this X, so that means I'm doing the COHA of the quiver with potential. So this guy is the associative algebra, and as a vector space, it's you get the complex cohomology of representation of your quiver with values in this vanishing cycle functor. And so Kontsevich and Soibelman, they define the Hall multiplication in this gradient vector space. So you get associative algebra. So the proposals of the conjecture. So one, the COHA, so this algebra, which I didn't define. So this thing X, categorified DT, homology of the modular space with value in this vanishing cycle functor. And the way they act is as raising operators, or by adding boxes. Okay, and this action holds for any stability condition for your moduli, for any stability condition. So often your modular space has an explicit quiver with potential description. So so then this action you get it for free. So I should write this theorem for part one. And part two, so the dream field double. of the COHA. Okay, so this also acts the categorified DT. And so this is the half of the double, and the other double is adding those lowering operators. Or by removing boxes. So you should think this is a universal symmetry algebra acting on the cohomology. Okay, so that's a conceptual way of describing which thing acting on the cohomology. And so we also have a proposal. So this factors through the sum shift again. And right, so when I talk about shifted Yangian, so this is already concrete. Maybe I say, so if I define things this way, so that's conceptual. So as long as you give me a quiver with potential and I can construct this string field double of COHA, it's automatically acts. And this shifted Yangian give you an explicit description of the algebra. So in terms of generator relation and the computations there. Okay, so maybe I'll make two remarks or shift it again. Right, so so for this perverse coherent sheet, for this one, right? So associated to those data, so we can define, we can associate a root system to it. And so when I say Yangian, so it's Yangian of the algebra associated to this root system. As examples, so you can glue those basic, we have those three fundamental building blocks. Three, the total space of -1, and also this one. The manifold. So you can do those things to get GL at m/n, so the super algebra m/n, depend on how many copies you use for this one, how many copies for that one. So this one has to do this Yangian of GL1/1 at. This has to do with Yangian of GL2. Right, so so that's Yangian for this root system and shifting. Against the conjecture. Yeah, so so this shifting, so my modular space, so the modular space depends on this preferred shift I'm taking and depend on stability condition. Okay. And how to shift the Yangian? So this shifting we write it as the intersection pairing. Of those data. So I'll just write V and the stability condition. right? So we have a concrete way to give me a Calabi-Yau toric threefold, and I know how to shift it, and giving a moduli space. Okay, and remark number 3 is so this general conjecture we checked it for those building blocks. Okay. Okay. So and the last part. So I want to talk about some interesting structures. Okay, so in my general proposal, there's a algebra acting on the cohomology, and it's actually utilized to other interesting structures in special cases. Okay, so special case number 1. So this has a special example. So this is the case has to do with AGT conjecture, generalized. So I'm taking, so let's say I'm taking X to be this ray. And so the favor in this case is the loop favor as discussed in Bond's talk. I'll denote the parentheses by B. So it was A. And the potential the favor. And so the potential is like this. And if you do derivative, we can give you the commutator of those 3 loops. All right, so that's the quiver with potential for the algebra. Now I choose B. I'm choosing a divisor inside this way, and so I will mark the multiplicity as N1 and 2 and 3. So that means I have N1, C2, X, Y, and N2, C2, plus. And those are the multiplicity for my divisors. Those divisors are torus fixed by P. And so now if I choose B to be O of D, okay, so I have some interesting modular space for that. And the theorem we showed. Okay, so we computed the COHA in this case. So the dream field double COHA is the non-shifted alpha Yangian of GI1 hat. So I will not define this, so I'll just write the symbol. And there's a concrete presentation for this one using general number relations. So we showed the alpha Yangian of GI1 X on the cohomology of this modular space. That's the moduli of spiked instants of universal. And so this spiked instant moduli has an explicit quiver with potential description. Maybe I'll draw the quiver. So I have 3 loop quiver. And with 3 framings. Go in and out. for each framing. So another way to describe this modular space is as representation of this frame the quiver with some stability condition. Okay. Right, so roughly, so you should think this modular space. So now I'm saying something not a mathematical statement. So roughly, so those are modular space parameterizing sheaves on C3, but supported on those three divisors. And C2. All right, and so now using this action, so using this action, so we are able to prove the VOA. So this action practice through the vertex operator algebra. So this is the VOA, depend on the framing, framing. So the way the framing label is I put the multiplicity of my divisor on the framing vertices, and 1 and 2 and 3. And so it affects through the VOA, which depend on 1 and 3. So this is the VOA at the common of Gayotto and Rapcak. So to prove the VOA action on the cohomological modular space, so it's important for us we know the free field realization for this vertex algebra, and that has to do with the co-multiplication of my associative algebra. Okay, so that's one theorem. That's the first special case. So let me. This is for one function. I should know the answer, but I forgot the name. I know the character given by eta function or something. That's the word. Okay. Okay, so there's another special case. So this is still work in progress. Right, so it's this PT modular space I talked about at the beginning. So I'm still taking X to the C3, and I fix the curve with outgoing additions to be principal of each number 1, number 2, number 3. So the curve is the X, and T fixed. And so there's a conjecture due to Rapcak. So they didn't say things this way. That's my understanding what they're saying in the paper. So first of all, there's one shifted Yangian of GO1 hat. This one shifting the same as the prediction in our proposal. So this thing X the invariant cohomology of the PT modular space. And so this action is for any partitions number 1, number 3. Okay, so you can see the triality this way. So I have a triple of functions. And how does it act to? So there exists algebra homomorphism. From the one-shifted Yaping Yang of GL1 hat to the differential operators of this. So I have three. So let me introduce. So if I write N1, so that's means number one is the partition of N1. So number two is the partition of N2, and number three is the partition of N3. So right, so the algebra homomorphism from Yangian to the differential operators of Cn1 plus N2, Cn3, and so this differential operator is invariant under Sn1, Sn2, and Sn3. Such that right, so such that, so I have this algebra homomorphism. If I write the image, that's a subalgebra. So, so if I denote the image, I think they call the image the column branch algebra, which depend on N1, N2, and 3. Branch. Okay, so such that if I look at the image, so this column branch algebra acts on the cohomology. Is a fixed asymptotic in my number. Right. So theorem. So so if I only look at one partition, so if I take lambda, I'll just write this lambda 0, 0, and other two partitions I don't want to be there. So by putting the work of Kodaira and Nakajima, and so this is really work of from Manifolds and Nakajima and Kodaira and Nakajima. So what is this column branch algebra is? So the conjecture says the following: this one shifted Yaping Yang GL1 hat subjects to the spherical rational Cherenkov algebra means write the idempotent as E H Sn. So that's my notation for spherical rational Cherenkov algebra. And what is this cohomology of the PT moduli? So it's this one. This is a Varman module now. So I'm taking, so for Sn, I have a partition lambda. So there's a irreducible representation for Sn. That's direct for Sn. And use this one, I can induce a representation for my Cherenkov algebra. And I put that important here. So that's the Varman module for the spherical Cherenkov algebra, and this thing is identified in the cohomology of number in this case. Right, so this the vanishing cycle function. Right, so the last 10 minutes, so maybe okay, so maybe I can discuss a bit about the case for two asymptotics. So, so let me just for simplicity, I choose this number to be the trivial partition, 0. It's so number 1, the partition of n, the trivial one. That's n. Okay, so in this case, so what's the common branch algebra? So we know following so the cohomology of the modular space. Zero E. So this one sitting inside this polynomial ring, this variable m plus m, and invariant under Sn plus m. And so this thing is isomorphic to this sub, denoted the sub by the capital lambda and m. And this one is in the paper of Est. Right, so they describe a sub in this polynomial ring. So this is called the generalized quasi-invariant. Meaning so for this one, so it consists of all those polynomials in variable x and y's. It's symmetric under the first m variables, symmetric under the last m variables. And for those cross terms, something like so this polynomial minus q as alpha. So this one, if it's invariant, means this two are the same. And so quasi-invariant means this thing is invariant under it's divisible under so there are some conditions control the cross terms, and the sub in here. And so we did a lot of computation, so those two have the same counting. So if I enlarge the target guy, I put in pose, we know the differential operators x there. C n plus m is n cross Sm, so x on this polynomial ring. And so what's a column branch algebra in this case? So it's a sub algebra. So it's the sub algebra of the differential operators that preserving this quasi-invariance. So that's our column branch algebra. And zero. Yeah, so this thing next. Cohomology. All right, so Right, so in general, it is not limit those two partitions, and they have a proposal which sub to take. And we verified some examples for those non-trivial pair of partitions. Okay, so yeah, maybe I don't go too deep for that, so I'll just stop it here. Thanks.